Okay guys, got a new microphone. Hopefully the sound's a little bit better than the previous videos. Now that we know something about vectors, we can start thinking about motion in more than just one dimension. So we're going to think now in this chapter about motion in 2 and 3 dimensions. So motion in 2 dimensions first, and then also 3 dimensions. So motion in 2 and 3D here. So let's start off by defining position in multiple dimensions. So let's start with a 3-dimensional position vector. Before we just gave position as some value of x or y or z, but now we could locate something in 3-dimensional space. So let me first draw our coordinate system here. Here's our y-axis. This is a y-axis here, and then we'll have an x-axis there. And here's a z-axis coming out like this. See? Now I'm really going to test my ability to draw straight lines. I'm going to give a vector r. I'll draw a vector r like that. Here's r. Vector. And I want to think how we could locate this position vector. So here's the thing we're locating. That's the position. That's the object right there, some sort of a particle. And this line is indicating the position of that particle. And just so you understand what's going on, to make the picture a little bit clearer, it might be helpful to kind of try to draw a little. Think of this as being part of a box, right? If I were to kind of draw this box here. I hope you can see these little blue lines I'm making, but this gives you some sense, right? We're going from one far corner to the other of this box. So this is our value of y there, and this is our value of z, and this is our value of x along these axes, right? So we could throw in our unit vectors here. This is the unit vector I, and this is the unit vector j, and here's our unit vector k. Magnitude 1 along the 3 axes. So here's our vector r, and so now we could write our vector r in unit vector notation, right? I could say r equals, so our vector r is just given by x I hat plus y j hat plus z k hat. So that's our position vector. Pretty straightforward, hopefully. Put a little box around this guy here. So this is just a vector that's locating the position in 3-dimensional space. Okay, so we could move on from there. Actually, before we move on from there, let's look at a sample problem actually, and then we'll come back to this picture. So over here, I've copied out a little problem from your textbook. Let's take a look at this problem and see if we can sort this out. It says a rabbit runs across a parking lot on a set of coordinate axes. Yeah, this is very funny. On which a set of coordinate axes has, strangely enough, been drawn. The coordinate meters of the rabbit's position as a function of time and seconds are given. So we're just going to think about a 2-dimensional surface. You can imagine a completely flat parking lot, and the x position at any time t is given by this expression here, and then the y position at any time t is given by this expression here. And it's asking us to figure out the position vector r at 15 seconds, and it wants us to do it both in unit vector notation and in magnitude angle notation. So let's make sure that we understand how to do this. So let's start off with thinking about it first in unit vector notation. So we're going to say that the position vector r at time t, right, as a function of t, is going to be equal to x at t times I hat plus y at t times j hat. That's what it means to put this thing into unit vector notation. And so I could go ahead and figure out what x is at time 15. So r, in other words, the value of r at 15 seconds. So r 15, I'm putting in 15 for the time in seconds. Just have to put in 15 here, and you should get 66 meters. So negative 0.31 times 15 squared plus 7.2 times 15 plus 28. That should give you 66 meters. So this ends up being 66 meters I hat plus and then if you plug in 15 here and here for the two t's here and here, then you should get negative 57 meters j hat. So that's the first part. Just plug in the values for t to figure out the position vector, and that's our answer to the first part in making the position vector in unit vector notation, right? That's it right there. The second part, then, we just have to convert this into magnitude angle notation. So how do I convert this thing here into magnitude angle notation? Well, let's figure out the scalar size of r, right? What is the value of r as a scalar size? And that's just going to be, just going to use the Pythagorean theorem, that's just the square root of 66 squared plus negative 57 squared. Do that out and you get 87 meters. And what's the angle of this thing going to be? That's a little interesting. What's the angle of this thing going to be? Well, if I were to draw these vectors out, right, if I were to draw them out, I would say 66 meters in the positive x direction. So that's 66. And then negative 57 meters in the y direction. So that's negative 57, like this. This is negative 57. And so my resultant here is going to look like this. It's going to be in that direction. And so if I want to figure out this angle here, if this is what I'm calling theta, then I'm just going to say that theta is the arctangent of negative 57 divided by 66. And that gives me negative 41 degrees. 41 degrees below the x-axis. It's worth noting there are other values that would, there are other angles that would give the same value, but if I draw this out, it makes sense that this is negative 41 right here. As a in terms of the picture, that angle looks like negative 41. 139, it could be 139 degrees. This is clearly not 139 degrees. Negative 41 is the only answer that makes sense. And so now I can say, in terms of magnitude angle notation, I could say r equals 87 meters and with an angle of negative 41 degrees. And I've completed the problem. Based on this explanation, we've got these two different expressions. We use them both to figure out the position vector. Hopefully that made some sense. Hopefully that was pretty straightforward. Now, what if I wanted to know the displacement? Could I come up with a displacement vector? So I could say, what is now delta r squared? So this is, maybe I should label this here. Maybe I should go ahead and make sure that this is the position vector. And now I'll do the displacement vector. What if this thing is moving in space, right? What if it moved to some other place? So what if my r, for instance, this picture is going to get very confusing very quick, but if I were to make my r now over here, right? So now there's a displacement from here to here. This is now delta r, okay? So this is r, maybe we could call this r1, and this guy here, this is r2. You could imagine we could make this box again and figure out where this thing is, but this is r1, this is r2, and this here is delta r. So how could I calculate delta r? So what is the displacement vector? So displacement vector delta r. And hopefully pretty straightforward. I can just treat the different directions independently. So I can say delta r equals x2 minus x1 times I hat plus y2 minus y1 times j hat plus z2 minus z1 times k hat. That's a k there. It's k hat. So we're just basically figuring out we're taking a look at the displacements of the three individual directions times their unit vectors. To think about how what that would look like in the picture, I don't want to clutter this picture up too much, but let's just say that this here, if we were to sort of extrapolate out in my picture, can I do this without making it too messy? I don't know. So let's say here's my value of z for R2, right? So this is z1 was here, z2 is here. So this right here would be my change in z2 minus z1. And then there's going to be some value, if I connect over here, there's going to be some value of x1 and x2 that you're subtracting along the x-axis, and y1 and y2 being subtracted along the y-axis. I hope that makes sense in terms of the picture. It's sort of, it's a complicated picture. I hope you can kind of understand what's going on there. So that then would be the displacement vector. And we could keep going with this, right? We could keep going. How would you define the velocity vector? If we had a displacement vector, could we come up with a velocity vector? Right? How would we define that? So I'm going to call that the velocity vector v. How would we define the velocity vector? Well, the velocity vector, we know that velocity is just the change in position over change in time, so I could call that dr over dt, which is the same thing as dx dt times I hat, dx dt times I hat, plus dy over dt times j hat, plus dz over dt times k hat. Okay, so this will now allow us to think about a velocity vector. And actually, we could go back, while we're at this, we could go back to this problem. The problem didn't ask us to do this, but what if we were curious, what if it's asking us now, I'm going to change the problem here. At t equals 15, what if we say, what is the rabbit's velocity vector? V. Okay, how could we come up with the velocity vector of the rabbit, right? How would we do that? So we know what the position vector is, so we just have to take the derivative of these two different expressions. So I'm going to go ahead and try to clear some space here. Oh, not what I want to do. Let's go ahead and clear some space, and we'll see if we can solve this problem. This new problem that we've invented. Clear a little more space here. It'll be very similar to what we did last time, but we've just got to take the derivative of the two expressions. So let's go ahead and see if we can figure out what the velocity is. So first of all, let's write v sub y, and hold on, or v sub x, right? V sub x is just going to be the derivative of this thing. What's the derivative of this thing? So that's negative 0.62t plus 7.2. That would be the expression for the velocity in the x direction, just the derivative of this thing. And the velocity in the y direction, derivative of this thing here. This is 0.44t minus 9.1. So now for any time t, I can determine the x velocity and the y velocity without too much trouble. So what are we thinking about? We're thinking about t equals 15 seconds. So now I could go ahead and say the velocity vector v is going to be equal to, if I plug in 15 there, I get, what is it, negative 2.1 I hat plus negative 2.5 j hat. Double check that on me. I put in 15 here and a 15 there. Negative 2.1 and negative 2.5. So that would be the expression of the velocity vector at 15 seconds in unit vector notation. And now if I wanted to do magnitude angle notation, just like we did before, I can say that the magnitude of the velocity, square root of negative 2.1 squared plus negative 2.5 squared. Which is going to be is that velocity going to be? Bear with me as I calculate this one. 3.3. I'm getting 3.3 meters per second as my velocity. And to figure out the angle, we're going to do a very similar thing that we did last time. We're going to say that the theta now is going to be the arctangent, in this case of negative 2.5 divided by negative 2.1. And that gives us an angle of a negative 130 degrees. Negative 130 degrees. So we could say now the velocity, ignore that. We're saying the velocity is 3.3 meters per second at an angle of negative 130 degrees. So that would be another way of expressing this. All right. So we've got now position vector, displacement vector, velocity vector. We could go ahead and do the acceleration vector as well. I'm not going to belabor this one because it's the same exact idea. We're just going to go ahead and take the derivative of the velocity vector. So the acceleration vector is going to be equal to, this is dv over dt. So that's, if I write it out as dvx dt times I hat plus dvy over dt j hat plus dvz over dt k hat. That will now give me the acceleration vector in 3 dimensions. So hopefully this makes sense. The idea here is we're using what we learned last chapter, a definition of a vector using both magnitude and position, and making use of this unit vector notation to define a position vector in 3 dimensions, a displacement vector in 3 dimensions, a velocity vector in 3 dimensions, and an acceleration vector in 3 dimensions. We'll put this to good use in our next video to talk about the motion of a projectile. We'll talk about something, a projectile moving through space in multiple dimensions. So that's next video.